Next, we're going to talk about breadth-first search, which is a completely different way to process all the vertices connected to a given vertex. It'll get the job done, but it has totally different properties that are useful in different ways for different applications. To understand breadth-first search, we'll start right out with a demo. So breadth-first search is not a recursive algorithm. It uses a queue as an auxiliary data structure. And it's also quite similar, quite simple to explain. So what we're going to do is we're going to put the source vertex on a queue and then repeat the following until the queue is empty. Remove the next vertex from the queue in FIFO order, then add to the queue all unmarked vertices that are adjacent to V and mark them. And just keep doing that until the queue is empty. Let's see how that works on our example. This is a smaller example, just a 6-vertex graph with 8 edges. So add 0 to the queue. So we just take 0 and put it on the queue. That's where we start. And now go into repeat until queue is empty, remove a vertex, add all unmarked vertex adjacent and mark them. So we dequeue 0. And then in order to process 0, we need to check all its adjacent vertices. So in this case, that's 2, 1, and 5. And again, the order depends on how the bag was constructed for vertices adjacent to 0. So we check 2, and that is not marked, so we have to add it to the queue. Then we check 1, that's not marked, so we add it to the queue. Then we check 5, and that's not marked, so we add it to the queue. So that's, we finished processing 0, 0's done. So now remove the next vertex from the queue. In this case it's 2, we're going to take 2 off the queue and process it by adding to the queue all the unmarked vertices that are adjacent. So to process 2, we have to check 0, 1, 3, and 4. We check 0, that's already marked, so we don't do anything. We check 1, that's also already marked, so we don't do anything. In fact, it's on the queue. We check 3, and that one is unmarked, so we mark it and add it to the queue. And then we check 4, that one's unmarked, so we mark it and add it to the queue. By the way, I didn't mention, but we're also keeping track of 2 auxiliary data structures for this. One is the edge-to array, which is the same as before. What edge did we use to get to this? So 4, we got to 4 from 2, and 2, we got to 2 from 0. So again, that's going to be a tree that gives us a path back to the source. And instead of marked, we also keep a more detailed information, which is the length of the path, because we do it because it's easy to do it. Okay, so 4, we check 4 and add it to the queue, and now we're done with 2. So now we have 1, 5, 3, and 4 are all in the queue, and we're going to process them. And since we've marked everything, all we're going to be doing now is checking vertices that are marked. So for 1, we check 0, and that's marked, and we check 2, and that's marked. So then we're done with 1. Next thing off the queue is 5, and we check 3, and that's marked, and we check 0, and that's marked, so we're done with 5. And then 3, we got to check 5, and then 4, and then 2, and they're all marked, and now we're done with 3. And then finally the last one, always the last one, everybody else is marked, it's connected. Check 3, check 2, it's marked, and we're done. So what this process, the result of this computation, again, is a tree rooted at the source, and we can follow back through the tree to get paths from each node to the source. And not only that, we can get the distance, the number of edges on the path from each node to the source. So that's a demo of breadth-first search, and next we'll take a look at properties of this algorithm. All right, so now we've considered two different methods for processing all vertices in a graph, and actually they're quite closely related, even though the computations are quite different. Essentially, depth-first search uses recursion, so it corresponds to putting unvisited vertices on a stack. Breadth-first search, explicitly, we put the unvisited vertices on the queue. And actually, breadth-first search solves another problem that often we want to solve, called the shortest path problem. Actually, the path that you get back from breadth-first search is the path from the source to the given vertex that uses the fewest number of edges. And we'll look at that in just a minute. And the idea is that the breadth-first search examines the vertices in the graph in increasing distance from the source. So let's take a look at that. So breadth-first search computes shortest paths, that is, it builds the data structure that we can answer shortest path queries from the source with, from S to all other vertices in the graph in time proportional to E plus V, the number of edges plus the number of vertices. And so let's look at why that's the case. So the first thing is, how do we know that it computes shortest paths? Well, the intuition is, and you can fill in the details, the queue always contains some vertices of distance k from the source, followed by some vertices of distance k plus 1. So they're on a queue. We're processing them in first in, first out order. So say we're at a state when all of these vertices are on the queue. We're going to have processed vertex 0. As soon as we get this one, we'll delete vertex 0 from the queue. And then when we're putting these adjacent ones on, we're adding the ones of distance 2. But we're not going to process any of those until we're done with the ones of distance 1 and so forth. So it's not hard to show that always you have either one of the two distances from the source on the queue. And that means the first time we get to a vertex, that's the shortest path to that vertex. And again, the running time, we only visit vertices once because we mark them. So it's time proportional to the number of vertices plus the number of edges in the graph. So that's breadth-first search properties. And then here's the implementation, which is simply code for the basic method that we outlined in pseudocode. So our private instance variables are marked, or in the demo we used dist2, but just for simplicity let's use marked. Edge2 then is how we get to the first vertex, and then the source. And so you have a constructor that builds those arrays same way as before, and then calls BFS. So BFS builds a queue, that's what it's going to use. It enqueues the source and marks the source. And then this is just in code what we said in words before. While the queue is not empty, we pull off the next vertex from the queue, call it V. For everybody adjacent to V, we go ahead and check. If it's marked, we ignore it and move to the next. If it's not marked, then we put it on the queue, mark it, and remember the edge. And again, this is an example of the power of abstraction and the utility of our design pattern. All we're doing in terms of the graph data type is being a client to go through all the adjacent vertices. But it allows us to implement this completely different algorithm in really an accessible way. So that's the implementation of breadth-first search. And then the client for getting the paths back is the same as for depth-first search. So here's an old application of breadth-first search in computer networks. It's very important. When you're communicating from one place to another, you want to get there in the fewest number of hops. This is the ARPANET, the predecessor of the Internet, as of July 1977. Things were slow, and computers were small and slow. It's important to do these things in small number of hops. And with breadth first search, you could take this graph and figure out the shortest way to get from one place to another. That's a typical application of breadth first search. Here's another one, so-called Kevin Bacon numbers. And nowadays, actually, you can type Bacon and an actor's name and get the answer to this. There's, if you're not familiar with it, you can become familiar with it by Kevin Bacon numbers. The idea is you have a graph where the vertices are actors, and the edge, you think of an edge connecting two actors if they were in a movie together. And so what you want to find is, given an actor, what's the shortest way to get to Kevin Bacon connected by, so we have edges for actors and edges for movies in connection if the actor's in the movie. So Buzz Morrow and Tatina Ramirez were in Sweet Dreams together, and these two actors were in this movie together, and so forth. And you get a way to Kevin Bacon from any actor. And this is another pop culture application of this is so-called 6 degrees, which you can get to anyone with 6 steps in this way. So that's all implementation of breadth first search on the Kevin Bacon graph, where we include one vertex for each performer, one vertex for each movie, connect the movie to all performers that appear in the movie, and the shortest path from Kevin Bacon to every actor. If you follow back through that path, you get you get the proof of the Kevin Bacon number for each actor, and we have implementation of that on the book site. So that's another example. And actually there's a maybe even older, so it's at least similar age example that mathematicians are fond of, and that's called the so-called Erdős number. So in this one, it's the nodes are mathematicians, and there's an edge if the two mathematicians have co-authored a paper. And Paul Erdős was a very productive Hungarian mathematician who traveled the world, co-authoring papers with people all over the world. A very interesting and prolific character who actually did quite a bit of research on properties of graphs. And maybe even more so than Kevin Bacon. The idea is he was so prolific that pretty much every mathematician has a pretty low Erdős number. So that's our second example of a graph processing algorithm, breadth first search.